Hello students, good morning. So here we are again with the chapter Wave Optics. So today we are moving to the second class of Wave Optics, in which we are going to study the proof of laws of reflection and laws of refraction using Huygens principle. Okay, so we have studied Huygens principle and I hope it is clear for you. You have gone through that video, and anyway today we are moving to the proof of laws of reflection as well as laws of refraction. So in the previous class I have told that with the help of Huygens wave theory he could successfully explain the phenomena such as reflection, refraction, then interference, diffraction, etc. So each thing here we have to study in detail. So first we are moving to the proof of laws of reflection. You know what is reflection and what are the laws of reflection, you know. That is, the angle of incidence is equal to angle of reflection. So we are going to prove the same thing with the help of Huygens wave theory, in which we have studied the wave front, then how to create a new wave front, then what are the laws behind Huygens wave theory, everything you know. So just before starting, I just want to summarize a few points. First of all, wave front you know. Then the direction of light ray is always perpendicular to the wave front. That is the main and important point that can be used in the proof. Then the second thing is, if you want to create a new wave front, what you have to do, because in a particular wave front at a particular time there will be a large number of points which will act as a source of secondary disturbances, and from this particular source you can draw arcs, isn't it? You can draw arcs because each wavelet is moving with the speed of the wave v, and in a time t or in a time gap of time t you can draw that distance, that is speed into that time will give you the distance, and you can form different arcs. And if you are covering it with an envelope, or if you are giving a common tangent to all the arcs, you will get the new wave front, isn't it? So that are the two important things that we have discussed in Huygens theory, which is used in the proof also. So now we will move to the proof of laws of reflection. So for that, first I am considering a surface. Okay, for the reflection I am considering a plane surface, you know. Let it be a mirror or a polished surface. Clear? Now I am considering two parallel rays. Okay, two parallel rays falling on this surface from a particular distance. Clear? Two parallel rays. So since they are rays, I have to put the arrow mark, very important. Now you know these are the incident rays. Clear? So here, if I want to draw the incident wave front, what is the direction? As it is always perpendicular to the direction of the ray, isn't it? These are the incident rays. And if you want to draw the incident wave front, since these are parallel rays, you know the wave front will be which shape? Plane. It is planar in shape. And that plane wave front will be perpendicular to the incident ray, isn't it? So for that I can draw a wave front like this. This is the incident wave front. So these are the incident rays. And this is the incident wave front. Okay, incident wave front. Clear? Now, let us give names for this. Let the surface be okay. Now, here you know this is a medium in which the light moves, or the light is in the form of a wave. It moves with a speed v. Okay, so let the speed of the wave can be considered as v in this medium, and let the time t is equal to 0. Okay, now you know this is a wave front, isn't it? So according to Huygens theory, we are proving this law of reflection with respect to Huygens theory. So in this wavefront, each point will act as the source of secondary disturbances. Isn't it? Each point will act as a source of secondary disturbance. Am I right? Okay. Now here you know, as this is the source of secondary disturbance or the secondary wavelets, we call it as secondary wavelets, it will start to grow, isn't it? Secondary wavelets will start to grow like this. Like this it will move. So I just want to take a point when the time t equal to 0 changed to time t equals t. Understand? Time t equal to t. So from time t equal to 0 to time t equal to t, I just want to see where the the wavelet reach. Okay. For that, you know this is a medium in which the speed of the wave is v and the time we considered is t. So what is the distance traveled? It is v into t. Okay. So here from this point, if I am considering at a distance of v into t, I can draw a arc here. Isn't it? From this point, I can draw a arc here, and from this point, I can draw a arc here. Okay. So these are the two arcs or the two arcs drawn for the different wavelets at a time t. Starting with t equal to 0. At a particular time t equals t, I have to place or I have to note a point where it reached. Okay. So I just assumed the distance, let the distance be v into t. So with this distance v into t, I can draw an arc here. Okay. And also since the velocity is same and time is same, I can draw at that particular, from C, if the arc is here, from A, the arc will be here. Clear? Now we joined the arcs. We drawn a common tangent for the arcs. So what about our new wavefront S? This is the new wavefront. Clear? This is the new wavefront. Understand? Now I name it as E. Okay. Now you know, for a wavefront, the ray will be perpendicular to it, isn't it? So if I draw the ray, how can I draw the ray? Here for this particular wavefront, I draw the ray like this because these two are perpendicular. And for this ray, I will draw, how I can draw? Because these two are perpendicular. So again, this is the ray. Is that clear? So here BE is the reflected wavefront. BE is the reflected wavefront. Then BR and AS are the reflected rays. Is much clear? Once again I will tell. Here we are going to have the proof of laws of reflection using Huygens wave theory. And according to Huygens wave theory, the direction of the ray is perpendicular to the wavefront. And also, if you want to draw the new wavefront from an existing wavefront, you have to take that particular distance with that speed and time, and then you have to form arcs. Okay, and if you are taking the outer envelope of the arcs, you will get the new wavefront that we have discussed in the previous class. So here we are considering a smooth surface, and then we are assuming two rays towards the surface. And for these two incident rays, first you have to draw the incident wavefront. Here you know this surface is like this. Okay, surface is like this. From the plane of the board, the surface is like this. Then here the incident rays are perpendicular to the incident wavefront. So this will be the incident wavefront which is perpendicular to the incident rays. So I have drawn here AC, which is the incident wavefront. AC is the incident wavefront. Clear? Now I have to form the new wavefront. I have to form a new wavefront. For that, we know that in this AC, in this wavefront AC, each point will act as a source of secondary disturbances. Isn't it? So here from this particular point, if I am drawing an arc with a radius of V into T. What is that V into T? Because speed of the wave in this medium is V and I am assuming a time T. Okay, first the time was T equal to 0, then I assumed a time T. So after that time T, where will the position? That is what I want to find. So with that value, I place here and I can draw an arc at this point B. Isn't it? When I draw an arc at the point B, from this point A also, I have to draw an arc here. I have to draw an arc like this. Clear? Then I joined these two arcs. That means I have drawn a tangent to that points. Okay. This tangent will be the new wavefront. And this is the reflected wavefront. So here BE is the reflected wavefront. BE is the reflected wavefront. Now I have to draw the reflected rays. You know the direction of reflected ray is perpendicular to the direction of wavefront, isn't it? For this wavefront, these two rays are perpendicular. So BR and AS are the reflected rays. Is much clear? Okay. Now listen. Now listen. This wavefront AC. AC is the incident wavefront. It is perpendicular to the incident rays, right? So here it is angle 90 degree, isn't it? Angle C is 90. Clear? Similarly, in this side, you can see BE, which is the reflected wavefront. So here BE, this angle E, is actually perpendicular. No, wavefront is perpendicular to the reflected rays. So here this angle E is also what? 90 degree. Isn't it? Now listen, this value, that is from C to B. What is the value? We have drawn an arc with a distance of V into T. So I can say BC is equal to what? V into T. Isn't it? BC equal to V into T. And also AE is equal to V into T. So BC equal to V into T. AE is equal to V into T. Clear? So these are the two sides, that is AE and BC are equal. Both are equal to V into T. Then the angles are also equal. Okay. So here first now we want to find the angles. Listen carefully. If I am drawing a normal here, this is my normal to the surface. You know this is the incident ray. So what is this angle? This is angle of incidence. So angle of incidence is the angle between incident ray and normal. This much is clear for you, isn't it? Now listen, this is what? This is a wavefront. Okay, this is a wavefront. I want to find the angle formed by the wavefront with the surface. Formed by the wavefront with the surface. How can I find? Because you know this value, this value is 90 degree. This value is 90 degree. So what about this value? This is 90 minus I. Clear? This is I because angle of incidence. Then this is 90. So this is 90 minus I. Now if this is 90 minus I, what about this value? What about this value? How can you find that? Because this is also 90, right? This is also 90. So this is equal to I. Once again, listen carefully. This is the normal. So this angle is I, angle of incidence. Okay. Now what about this angle? Because this is 90 degree. This is 90 degree. So this is 90 minus I. So you got two angles, I and 90 minus I. Now I want to find the angle made by the wavefront with the surface. For that, again, this is 90. This normal and this surface is 90, right? So I got 90 minus I here. So the remaining will be I. So what about the angle? Yes, angle made by the wavefront with the surface is also I. Clear? So angle of incidence, again I is also the angle made by the wavefront with the surface. We have studied that it is the angle made by incident ray with the surface. With respect to wavefront, if I am saying, I have to say, incident ray with the normal and wavefront with the surface. Understand? This much clear. Now here also we can find like that, because this is the incident ray and this is the reflected ray, isn't it? So here, what is this? This is angle of reflection. Angle of reflection. Now what is this angle? What about this angle remaining? Because this is 90. This is 90. So this is 90 minus r. Isn't it? 90 minus r. Again this much is 90. So what is this angle? This is again r. Clear? Okay. Now let us consider two triangles, right angle triangles. Which are they? First is, listen carefully, ACB. This one, ACB. Okay. Now the second one is that is AEB. AEB. Clear? So in this triangle ACB, you know this is 90 degree. Okay. Then here in this triangle, angle E is 90 degree. Clear? Now we already said that BC and AE are equal to VT. BC and AE are equal to VT. That is, these two sides are equal, which is VT. These things you know. Now listen. Here I am taking sine I. Sine I. So what is sine I from the figure? Because you got this angle, no? This angle as I, isn't it? Here you got this angle as R. So what is sine I? Sine I is opposite side by hypotenuse. So sine I is equal to, opposite side is BC divided by hypotenuse is AB. Isn't it? Also there, sine R is equal to, what is opposite side? It is AE and hypotenuse is AB. Isn't it? So we already told that BC is equal to AE. BC equal to AE. Therefore, I can equate these two because the denominator part is same. The numerator is also same. So sine I is equal to sine R. If sine I equal to sine R, I can say that I is also equal to R. Isn't it? So angle I equal to angle R. In this way you can do. Otherwise you can take like this and you can apply the congruence theorem. These two triangles are considered as congruent since these angles are same, 90-90. Then sides are same. So the opposite angle to the side, the congruent side is also same. In that way also you can take it as I equal to R. Two ways you can prove. Understand? So here our first law of reflection. Understand? So first construction you should be clear with that. Then the formation of angles. Okay. Then applying here. Simply taking sin I and sin R and equating, you will get I equal to R. Okay. So this is the first law of reflection. Now what about the second law? Second law you have studied, that is the incident ray, reflected ray and the normal lie on the same plane. Listen there. Here you know this AB. AB is the plane surface. So this AB is actually like this, isn't it? Like this. Okay, that is to the plane of the board, AB is perpendicular. To the plane of the board, AB is perpendicular. Okay, then what about the incident wavefront? Incident wavefront is actually like this, right? Again, this is also perpendicular to the plane of the board. What about the reflected wavefront? That is also perpendicular to the plane of the board, isn't it? So incident wavefront, then the surface and also the reflected wavefront are perpendicular to the plane of the board or plane of the paper. Now what about the incident ray? Yes, incident ray is perpendicular to the incident wavefront. Am I right? Then reflected wavefront and reflected rays are perpendicular. Also normal is perpendicular to the surface. Okay. So now you can say that incident ray, then reflected ray and the normal lie on the same plane. Understood? So thus we proved the laws of reflection. Once again, here if you are considering the incident wavefront, reflected wavefront and the surface, these three are perpendicular to the plane of the board. Again, incident ray is perpendicular to the incident wavefront. Reflected ray is perpendicular to the reflected wavefront and normal is perpendicular to the surface. So, you can say that the incident ray, reflected ray and the normal lie on the same plane. Clear? Okay. Now, we are moving to the second proof, that is proof of laws of refraction. First one is clear for you. Now, laws of refraction, mainly the Snell's law. You know Snell's law, that is the ratio of sine of angle of I to sine of angle of R is a constant. And what is the name of the constant? As it is refractive index. Okay. So now we are moving to the proof of laws of refraction using Huygens theorem. Okay. So for that I am considering a boundary between two media. As you know, refraction means the bending of light from when light travels from one medium to the other medium. Okay. So in two medium, the light will be having different speeds, isn't it? In reflection, we considered only a single medium in which the speed of the wave or speed of the wavelet is considered as v itself. But in this case, we are having two media. That is, first media we will consider it as a rarer media and the second one is a denser media. Okay. So here it is having a speed v1 and here it is v2. Here the refractive index is taken as n1 and here it is n2. In some textbook it will be mu1 and mu2. Don't get confused, both are okay. Now here I am considering two parallel rays. Two parallel rays. Okay, two parallel rays falling on this boundary, and here you know these are the rays. So if you want to draw the incident wavefront, similar to the last proof, you know it is perpendicular to the ray. So I can draw an incident wavefront like this. This is the incident wavefront. Clear? I will name it as A, B and C. So here AC is the incident wavefront. Okay. Now you know this is a medium having a speed v1. So here let the time be t equal to 0, and after a time t, when the time turns to t, I just want to find the distance travelled. How can I find? If the speed is v1 and the time is t, the distance travelled by this wavelet is v1 into t. Isn't it? v1 into t. And you know here this is a source of disturbance. This is a wavefront and each point will act as a source of secondary disturbance. So from here C, it will move to a distance of V1t, isn't it? In the first media, V1 into t. So I can place here and draw an arc at the point B with a distance of V1t. Okay. Now this is rarer medium and this is denser medium, and so V1 is always greater than what? V2. Isn't it? Speed of light in rarer medium is greater than speed of light in the denser medium. We have studied that. Now from this point, if we are drawing an arc here, at the same time t, you can draw an arc from A somewhere here. Why? Because this is greater speed, right? So V1t is not equal to V2t. Understand? We are assuming a time t and we consider this V1 as the speed of this medium. So the distance traveled be V1t. We are assuming like that and we are drawing an arc with that distance. We got an arc at the point B. But from this point A, this is also source of a secondary disturbance, right? So from this point A, if I want to draw an arc, I'll get somewhere here only. Because this distance V1t is not equal to V2t. Both speeds are different. V1 is more than V2. So it will travel only a smaller distance when compared to this. Understand? So here you are getting the arc. From this point A, if you are drawing, you will get here. Okay. Now joining these two. This is your new wavefront. Understand? So if I am drawing a normal like this. Okay. Now this is a new wavefront. So you know the direction of the reflected ray will be perpendicular to the direction of the wavefront, isn't it? So how will you draw the wavefront here? Here it is the wavefront because both are perpendicular. You can see that. Okay. Here this is the wavefront. Both are perpendicular. Understand? So in this way, I can draw the new wavefront, which we call it as the refracted wavefront, and these are the refracted rays. It is moving from a rarer medium to denser medium, so surely the speed will be less and it will bend towards the normal. Is much clear? Once again, here we are going to have the proof of laws of refraction, mainly the Snell's law we are concentrating. That is sin I by sin r is equal to a constant, or is equal to a constant called refractive index. We call the law as Snell's law. Okay. Here we are taking two parallel rays falling on a boundary which separates two media, having two speeds V1 and V2. This is a rarer medium and this is a denser medium. Now these rays, when it fall on the boundary, here we are drawing a incident wavefront which is perpendicular to the direction of the incident rays. Now our aim is to draw what? A new wavefront. For drawing a new wavefront, here we are assuming a distance of V1t, because each point is a source of disturbance. So if you are drawing means you will get concentric like this, no? This type of wavelets will come like this. So we are just taking a time interval of t, and in that time how much distance it is traveling. So in the first medium it is V1t, and in the second medium we assume it as V2t, but V1t is not equal to V2t. Why? As both speeds are different. Here it is more, here it is less. So the distance traveled here will be more when compared to distance traveled from this point to that arc. Okay, so here we can draw two arcs, and I drawn a common envelope for the arcs, so that I got a new wavefront, which is our refracted wavefront. Now the ray I can draw because the ray is always perpendicular to the direction of the wavefront. So this is my refracted ray. Here this is my refracted ray. Now we are moving to find the angles. Okay, the same way like the last proof. Listen carefully. So this is the angle of incidence. This is the angle of incidence. And you know this is 90 degree, isn't it? This is 90 degree because this is the wavefront. So this will be 90 minus I. Okay, I want to find the angle between the wavefront and the surface. So now this is 90. So what is this angle? If this is 90 minus I, this will be I. Clear? So I got first angle, that is angle of incidence, which is the angle between the incident wavefront and the surface. Also angle of incidence, if I am saying with respect to ray, angle of incidence is the angle made by incident ray with the normal. Clear? Here with respect to wavefront, the angle between the wavefront and the surface, that is also I. Okay. Now again, here you know this is angle of refraction, isn't it? This is angle of refraction. So how will you find this angle? This is the wavefront and this is the surface. How will you find? Because this is what? This is the wavefront and this is the ray, so it is 90 degree, and so this is 90 minus R and this will be R. Clear? Clear? Okay. Again this is 90 degree. This is also 90 degree. Everything clear. Now we will move to the mathematical part. That is, first of all, considering two triangles, triangle ACB and triangle AEB. Okay. In triangle ACB, you can see that angle C is equal to what? 90 degree. And there what is sine I? What is sine I there? Sine I is opposite side by hypotenuse, isn't it? Opposite side is BC, by hypotenuse is AB. Clear? Now in this triangle, that is triangle AEB, this is 90 degree, isn't it? Yes. Now here, what is sine R? Sine R. Sine R is AE divided by AB. Okay. Now I am taking the ratio here, that is sine I by sine R, which is BC by AB divided by AE by AB. AB got cancelled and it is BC by AE. Now what is BC? Listen, what is BC? Yes, BC is V1T, isn't it? And what is AE? AE is V2T. Clear? So, sine I by sine R is equal to V1 by V2. And this is a constant, right? V1 by V2 is a constant. Okay. In terms of refractive index, if I want to say, I can write sine I by sine R is equal to V1 by V2, which is N2 by N1. Isn't it? Which is N2 by N1. Clear? So we proved what? Snell's law. What is Snell's law? Sine I by sine R is a constant. Clear? We have came to the proof of law of diffraction. The next law is same as before. That is the incident ray, refracted ray and the normal lie on the same plane. That is same as before. Okay. Here once again the construction you understood. Then moving to the angles. Angles also same as laws of reflection. After that you are taking sine I and sine R from these two triangles. Then taking the ratio BC and AE you will get. So you will write the values because AE is V2T, this is V2T and this is V1T right there. So V1 by V2 is a constant. So sin I by sin R is V1 by V2 which is a constant. In terms of refractive index, sin I by sin R equal to V1 by V2 which is N2 by N1. Understood? So this is all about the proof of laws of diffraction. So write it and study. Both the proofs you have to write it and study. Only then you will get the idea. It's actually very easy. Just understand the concept and then apply there. You can easily study it. So go through it and if you have any doubt, contact me. Okay. So thank you and have a nice day.